Hello everybody and welcome back. Today we'll be talking about rate laws in chemical reactions, which essentially describe how the concentration of substances in a chemical reaction change over time. So there are three different types. The first one is zeroth order, which is where the rate equals the concentration to the zeroth power times a rate constant K. And this rate is equal to the negative change of the concentration with respect to time. Because, for example, if you had a chemical reaction, A plus B goes to AB, and you start with a certain amount of A and a certain amount of B, over time, those concentrations will decrease because they're making this product AB. And so there are also what are called integrated rate laws for each of these reactions. So you have zeroth order integrated rate laws all the way up to second order. And so in this video, we will be deriving these integrated rate laws. So what we can say, first off, is taking this K and this negative derivative of the concentration of A with respect to T, and we can set them equal to each other. So K equals negative D concentration of A with respect to T. And then what we can do is called a separation of variables, because this is a differential equation. So what we can do is multiply dt over to the other side, and so we can say K dt, and we can move the negative sign over as well. So negative K dt equals D concentration of A. And so what we have here is on this side, it's a differential equation with respect to T, and on this side, it's a differential equation with respect to the concentration of A. So if we integrate both sides, then we can use different variables in order to integrate. So if we rewrite this as D concentration of A equals negative K dt, and we integrate both sides, what we have is the integral from the starting concentration, which is concentration of A naught, all the way up to whatever concentration you want, dA. And so really this is a 1 in the integral right there, equals negative K, and this is the integral from the starting time, T naught, all the way up to whatever time you want, dt. So in this case, you have the integral of 1 is just whatever variable, so that is the concentration of A, but it's a definite integral. So we're going to evaluate it from the initial concentration all the way up to the final concentration. And so that equals the integral of negative K, and since K is not the same variable as what we're integrating, then it just is a constant. So the integral of a constant is that constant times the variable. But of course, this is evaluated from T naught to T. So what we get is that it's the concentration of A minus the concentration of A naught, and that equals negative K times T minus T naught. But we can rearrange this, and also we can say that T naught is equal to 0, because we can say that the time that it starts is at T equals 0. So what we end up with is that let's go over here, concentration of A equals negative KT plus the starting concentration. And so this is the integrated rate law for zeroth order reactions. Now what we can also find is the half-life of this reaction. And so the half-life occurs T1/2 when the concentration of A is equal to 1/2 the concentration at the beginning. And so we can substitute this into this equation. So we can say that the 1/2 of the initial concentration equals negative K times T1/2 plus the initial concentration of A. And what we can also do is rearrange this equation. So we can subtract 1/2 initial concentration from both sides, and we can move this term over so that we get K times T1/2 equals 1/2 concentration of A naught. Dividing by K, we see that T1/2 equals the concentration of A naught over 2K. And so this is the formula for the half-life of a substance in a zeroth order reaction. Next, we have first order reactions, where the rate is equal to the constant times the concentration of A, or just the concentration of that substance, to the power of 1. And this also equals this negative change in concentration with respect to time, because it works the same way, where the amount of that substance in the reaction is decreasing over time because it's forming product. And so we can do a very similar process. We can say that negative dA with respect to T, make that a little clearer, equals K times the concentration of A. And we can use a very similar separation of variables, except this time we have to notice that this A is the same thing as this dA. So we can rearrange this and move the negative sign by saying that 1 over the concentration of A dA equals negative K dt. And so very similarly to the last one, here we have a separation of variables where this side is in terms of the concentration of A and this side is in terms of T. So we can likewise integrate both sides. We can say that this one is the integral, again, from the concentration of A naught to the concentration of A, whatever that may be, 1 over the concentration of A d concentration of A, and this side from T naught to T, negative K dt. And so on this side, we have the integral of 1 over the variable, which is always the natural log of that variable. So we can say that the natural log of the concentration of A evaluated from the concentration of A naught to the concentration of A equals, on this side, again, it's just a constant. So we have negative K T evaluated from T naught to T. And so bringing this up here, we have that the natural log of A minus the natural log of A naught equals negative K times T minus T naught. And so again, we can say that T naught is equal to 0 because it's the starting time. And so rearranging this, what we have is that the natural log of A equals negative KT plus the natural log of A naught. I'm sorry, the naught should be outside of that natural log. And so what you have here, this is the integrated rate law for a first order reaction. So very similarly to the last one, we can also find T1/2, which is the half-life, and that occurs when the concentration of A is 1/2 the initial concentration, because half of the amount of that substance has disappeared. It has formed into product. And so what we can say is that natural log of 1/2 the concentration of A naught equals negative K T1/2 plus natural log of the initial concentration. And so this term and this term we can combine. So if we move this over to the other side, we can say that the natural log of 1/2 of the concentration of A naught minus the natural log of A naught equals negative K times T1/2. And so when you have a natural log being subtracted from a natural log, this is just a rule. What you can say is you can combine them and say that it is this term over this term. So you have 1/2 concentration of A naught over the concentration of A naught equals negative K T1/2. And so for this, we're also going to use another log rule. So if we divide by -1 or multiply by -1 on both sides, we get that the negative natural log of all of this equals to K times T1/2. And so this is a rule: when you have a negative sign in front of a log or anything outside of a log, you can raise it to the exponent of what's on the inside. So if we were to take this, for example, we would get that the negative natural log of that is just the natural log of the reciprocal of all of this. So concentration of A naught over 1/2 concentration of A naught. And so these will cancel out. This is 1 over 1/2, which equals 2. So if we come back up here, this is really just the natural log of 2 equals to K times T1/2. And we see that T1/2 equals the natural log of 2 over K. And this is the half-life for a first-order reaction. And here we have the last one, which is a second order reaction. So we have that the rate is equal to this constant K times the concentration of the substance squared. And yet again, this is also equal to the negative change with concentration with respect to time. And this is because the reactants are decreasing as the products are increasing in this case. So what we can say very similarly is we have K concentration of A squared equals to negative D concentration of A, that clearer, with respect to T. So before we can integrate, what we have to do is separate the variables. So if we multiply by dt on this side and divide by concentration of A squared, then what we get is K dt, we can move the negative sign over, equals 1 over the concentration of A squared d concentration of A. And so we can integrate both sides. So we have the integral from t naught to t of negative K dt equals to the integral from concentration of A naught to the concentration of A of 1 over the concentration of A squared d concentration of A. And so what we have here is an integral of 1 over the variable squared. This is a little bit difficult, but what you can say is, so if we go up here, the integral of 1 over x squared dx. So this is the same thing as x to the negative 2 dx. And so similarly to any other integral, we can just apply the power rule. So what we can do is we can add 1 to the exponent, so that'd be x to the negative 2 plus 1, and so that would be x to the negative 1, and then we multiply by this exponent over here. So it's negative x to the negative 1, which is negative 1 over x. So coming back over here, we have that negative 1 over the concentration of A, evaluated from the concentration of A naught to the concentration of A, equals negative K times T, evaluated from T naught to T. And this is because, again, it's just a constant, and so a constant, the integral of a constant is that constant times the variable. So over here, what we really have is that negative 1 over concentration of A minus, so that's a plus 1 over the concentration of A naught equals negative K T minus T naught. Again, we can say that the starting time is 0. So what we can also do is multiply by negative 1 on both sides to get this K to be positive. So we can say that instead of having this, we'll change the signs. So 1 over the concentration of A minus 1 over the concentration of A naught equals positive KT. And then rearranging, we see that 1 over the concentration of A equals KT plus 1 over the concentration of A naught. And this is the equation for the second order integrated rate law. So the last thing that we have to do with this is find the half-life. And so again, that T1/2 occurs when the concentration of A equals to 1/2 the initial concentration. And so substituting that into this equation, we see that 1 over 1/2 concentration of A naught equals KT 1/2 plus 1 over the concentration of A naught. And so this is 1 over 1/2, so that's just 2 over concentration of A naught equals KT 1/2 plus concentration of A naught. So if we subtract this from both sides, we see that 1 over the concentration of A naught equals KT 1/2. And so rearranging, we see that T 1/2 equals 1 over K times the concentration of A naught. And this is your equation for the half-life of a second order reaction.